I'm here. See, yeah. Should I just like start talking a bit? Hmm. Uh, hey guys, good evening. We'll start in 5 minutes. No idea, dude. How are we supposed to know if anyone heard him? Hey, good evening to everyone. Welcome to NeuRes Day 3. Today we have Tejas and Harshit as our speakers, and we'll be learning about convolutional neural networks. Also, the attendees are requested to stay till the end to receive swags and the sponsor prizes. Thank you. Tejas?
So, good evening, everyone present here. Welcome to the day three of our deep learning series, NeuRes. I hope you all enjoyed the previous day sessions that took place on 16th and 17th. And we are looking forward to sharing this session with you guys and making your time worthwhile and fruitful. We hope you'll enjoy this session. So, the topic we'll be presenting today is on convolutional neural network. The speakers for today are myself, Tejas Chintala, and my fellow co-speaker, Harshit Agarwal. I'll walk you through the agenda for today's session. We'll be exploring the basics of a convolution neural network and its importance and its usages. We will even explore the operations that are performed within the CNN structure and how and the different layers of the CNN and its architecture, as well as the different types of CNN models used in the present day. At last, we'll be implementing these concepts via a hands-on session through Google Colab, which this will be a really interesting session. So let's get started. Here we go. So what is CNN? Like before I start, I want to know how many of you guys are familiar with CNN or have heard about it. Like, guys, let me let's start. So, like in CNNs are a class of deep neural networks which are able to classify or recognize the features, particular features from the images, and which are widely used for visual images as well. And we see its applications. It ranges from the video recognition, image recognition, medical image classification, NLP, computer vision. And when I talk about the term convolution, what does it signify? Like, what does it denote? So it's a mathematical function, or it's a linear operation where there are two functions, and we multiply this together to get a third function, and which expresses how the shape of one function is modified by the other. If I say it in simple terms, I'll say it as if we get two images. Like if I want to find the features, I'll be representing it as a matrix, and I'll be multiplying it to get my output so that I can get that particular feature from the image. So like why do we use CNN? Like before we talk about CNNs, but why do we use it? We have so many other neural networks like feed forward, artificial ANNs, but why do we use CNN for, and what purpose? So like let's think of a scenario like where we are working on an image recognition project or something. So like there we encounter many images of different pixels, different dimensions. So like for lower dimension images we can use neural networks, but when it comes to higher dimensions, large pixel value images, so when we pass those into our neural network, we face a lot of time. Like there's a lot of time constraints. It consumes a lot of computational power, so which is not feasible at all. So like if I give a scenario like if I have an image of 64 cross 64 into 3 size image, here the here the number 3 signifies the number of channels, which is the RGB channel, and 64 into 64 represents the size, the height and width. So if we pass away this image into a neural network, we'll be getting the input parameters of 12,288 parameters, which is fine for which can be taken by the neural network. But if we get the image of higher resolution, so like 1,000 to 1,000 into 3 size image, So it will take in as 3 million input parameters. So it is really not feasible. It takes a lot of time and a lot of computational power. So if I tell in layman terms, CNNs, they try to extract the feature of the image and converts it into lower dimensions without losing its characteristics. So let's moving on. Like this is the overall pipeline of CNN structure. Like here I can see like I'm giving the input image as a car image of to my CNN structure, which is highlighted with the blue outline. You can see there are a lot of different layers like the convolutional layer, pooling layer, fully connected layer, and these layers are able to predict which what is the input image. Like you can see the car as a predicted class. So we will be talking about these layers in details in the upcoming slides. But before we go further and analyze the different layers, we need to understand the mechanism that takes place within these CNN layers and how it works. Like the most important term I would say is kernel over here, or the filter. So in CNNs, or convolutional neural network, the kernel is nothing but a filter that is used to extract the features from the image. So like it is a matrix that moves over my input image, and it performs a dot product with the particular subregion of the input data, and it helps us gives the output as of the matrix. It also gives the output as a matrix of dot product. So as we see over here in my picture over here, I have a image matrix of 5 cross 5 image matrix, which is, and we are having all the pixel values. And if I pass a filter over here, I have a 3 cross 3 filter matrix over here. If I perform my matrix multiplication, as you can see from from over here, it is performing multiplication for each and every sub part of the image, and we are getting another 3 cross 3, which this is called as a feature map or convoluted feature. So we are performing that to reduce the size of the image and to get the especially extracting the particular features. Like if you see over here, like from the animation as well. So the kernel slides over the 2D input data, performing the multiplication with the part of the input it is currently on, and getting the single output pixel over here. And this kernel, this process is taking place over for every location. It slides over the our input image. So this is the like basic mechanism of how our CNN works, or what goes within the CNN layers. Moving on, uh, striding. So like we can even like control how our kernels are sliding over our input image or input matrix. So when we talk about stride is like it mentions the number of pixels which shifts over the input matrix. Like for example, like if I it tries to skip some part of these locations of the kernel. Like if I give a stride of 1, so my kernel will be shifting 1 pixel apart. If I give a stride of 2, it will shift 2 pixels apart in our image and helps to extract the features as. So this is striding. So there's one tricky issue when we are applying CNNs, is that like there's a chances that we might lose some of the important features which are there at the perimeter of our image, or the peripheral part of the image. So there's a chance like sometimes our kernel or the filter does not fit perfectly into our input image. So here we have some options, like we have an option of padding. So padding is like if it preserves this original size of the image, and what it does something clever is that it adds fake pixels to our perimeter of the image. As you can see over here, it adds fake pixels of the value of 0 over across all the image. And when we are like when the kernel slides over the input image and performs the metric multiplication, we are able to get the exact same size, and we are able to like preserve the features also, as well. Like there's some instances as well that my image, the peripheral part of the image contains more important features than the middle part. So yeah, like so to preserve that and to uh, extract those features, we use the padding option over here. And if I give a scenario over here, like this is a this is how my padding works. So my blue matrix signifies the image, like denotes the image, and the highlighted part is the kernel sliding over it. And there's fake pixels which are added to the perimeter of the image, and we are seeing how the kernel slides over it, and it's able to extract the peripheral features of the image and helps to preserve the same size of the image as well. So this is like a very important important mechanism I can say. So these were the important mechanisms which go within the CNN structure. We needed to understand it before we discuss the different layers of CNN. So right now, after discussing it, let's discuss about the different layers as well. So the different layers of CNNs are the input layer, we have the convolution layer next, pooling layer, fully connected layer or the FC layer, we have the dropout layer as well, and the output layer, which gives the predicted class. If I show it in order, how the layers are set up. So this is the order, like we give the input, there's a convolution layer, pooling layer, as I mentioned. Let's get into it. So very first layer is the input layer. So the input layer in the CNN, it should contain the image data as well. We are giving the image matrix to our input layer, and it should contain like a three-dimensional matrix, which is reshaped into a single column. Like for example, I have a 28 into 28 size image matrix. So we need to convert into 784 into 1 vector before feeding it into an input. So like if we are given a scenario, we have a M training. If we have M training examples, then our dimension of the input will be 784, comma M. And I've given a code snippet over here, like how we can give the image to our CNN model. We will be discussing this code in our hand session in details. Next layer is the convolutional layer. So this is the first layer I can say, like it is used to extract the various features from the input image. So I already discussed how the kernels, strides, and padding works over here. So this is the main mechanism which works over here in the convolutional layer. So I can say that there's an input image and the filter, of course, and then we perform the dot matrix or product over this input image and the filter, and we are able to get the respective feature map. And if I say here also, I've added a code snippet as well. We can say like I've added a stride of 2, which with a RGB channel image and a size of 32 pixels. Our next layer is the pooling layer. So pooling layer section is basically it's used to reduce some number of parameters when our images are too large. Or too large, or we need to extract some more features within a convoluted feature map itself to get the predicted class of our image. So there are like many like steps as well. So the primary aim of this layer first is to decrease the size and to even reduce the computational cost. So there are main two main types of pooling process, which one is the max pooling layer, which takes the largest element from the feature map, and the average pooling layer, which takes the average of the elements in the image section. You can see from this image, if I have this image over here with all the pixels pixels specified. So like if I want to so if I uh, what do you say passing it to my pooling layer, so with a filter of 2 cross 2 and a stride of 2, my kernel will shift over these images with obviously a stride of 2. It will shift to 2 pixels apart, but to reduce it, it will find the like for max pooling layer. If I give an example for the max pooling layer, for this subpart, this is subpart of the image. What is the maximum value of it? From 1156, the maximum is 6. So it takes to our kernels filters 6 over here. Same as for this part of the image, it gives us a value of 8, and for the respective as well. What do you say? Respective subpart of the image as well. There's 3, there's 4. So this is how my pooling layer works. It reduces my feature map even further, and it specifies like what features I can like extract. This is a max pooling layer. Like if I talk about average pooling layer as well, like for the same parameter stride for the stride, if I set the stride 2, and if if my kernel is 2 cross 2 matrix, so it will find the average of this subpart and it will give me the values of it, respective values. This is how the average pooling layer works. Excuse me. Yes, sorry. Moving on to the next layer, which is the fully connected layer. So after I get my features, after I perform, if I get the important features from our images, I'll be passing it into my fully connected layers. So which consists of weights, biases, along with the neurons, and it is used to connect the neurons between two different layers. And like when and it is basically this layer is placed between the output layer and our last few layers of the CNN architecture. If I give us if I give This is our main structure of the FC layer. We when we are given the When we get the convoluted feature or the feature map, so we need to flatten our matrix into a vector. We can only after we convert into a vector, we then only we can pass it into this neural network. As you can see, there's the input layer which 4 parts, and this is a hidden layer, and it gives us 3 options, which is the output layer. So the dropout layer, I feel, is the very important layer. So like sometimes when we pass the features into FC layer, there's chances of overfitting in our training data set. Our model might overfit. So to overcome this problem, we add so this dropout layer will be dropping some of our neurons in our neural network during the training process, and it results in a reduced size of the model, and it basically prevents overfitting. And like if I give a dropout value of 0.5, if my 50% of my nodes will be dropped off randomly from my neural network. If, so here, if you here also I've added a code snippet, a small code snippet, and let's move on. Activation layers. So activation layers is a node that is put between the neural networks. So it helps to decide if a particular neuron would have to fire or not, and it is used to determine the output of a neural network, like yes or no, or whether my image is a cat or a dog or a car or a truck. So it maps like a resulting values in between 0 to 1 or -1 to 1. It depends on the function as well. And it's used to learn and approximate any kind of continuous and complex relationship between variables of the network. So like there are different types of activation layers. We have the most important value layer and the common layer. It's a common activation function. We have the softmax, sigmoid. This is some of the activation functions, as I mentioned. The sigmoid, tanh, relu. I would like to explain relu. I would like to explain relu this because one of the most important activation functions. It's the most widely used as well. So and these are the graphs for each and every activation function. So like for a relu, if I to give it gives an output of x when if x is positive, and it gives the output of 0 otherwise, like for negative values as well. And it's often used for it's in hidden layers in our neural network. Then we have the sigmoid function, which is also called as the logistic function. It is traditionally a very popular as neural activation function as well. So the input which it accepts from the function is transformed into a value between 0 and 1 range. We even have the softmax layer, which is it predicts multinomial probability distribution, which means that it is used for multi-class classification problems where class membership is required on two class labels, on not two, more than two class labels. Like if I have an image of car, I want to um, predict what it is between a car, whether it's a car, truck, tractor, and or anything like. It's a more than two class labels. So these are the different layers of CNN in brief. But we can uh, we can even add many layers to one models. That's why we will be discussing some of the types of the CNN models which are used in the present day. One of the most important model it's a ground one of the most important model is the layer net. So this was a groundbreaking algorithm, and it was one of the particular first of its kind in terms of object classification. So it was basically trained to classify handwritten digits from 0 to 9, which is our MNIST data set, and it comprises of 7 layers, 7 convolutional layers, which is all made up of trainable parameters. Moving on to our next model, LXNet. LXNet was the winner of the ImageNet competition, 2012 competition, the ILSVRC 2012 competition to be precise. And its network is similar to the LayNet architecture, but the only difference is it has a large number of filters compared to our original LayNet architecture, and it was able to classify among large classes of objects. And another difference is it used the dropout layer instead of our regularization technique to deal with the overfitting of the model. And it consists of 5 convolutional layers. Then we have the Bgg Net 16 model. This particular architecture was the runner-up of the ImageNet competition 2014, and it's an improvement over the AlexNet as it replaces the large kernel size filters. Like for our AlexNet architecture, we had a kernel of 11 in the first convolutional layer and a kernel of 5 in the second convolutional layer, respectively. But it replaced those kernels with a 3x3 kernel size filters, one after the another. Let's move on to ResNet models. This was one of the most groundbreaking development in the field of CNN architecture, which was the Resonator residual networks. So this is based on the idea of skip connections, and it implements heavy batch normalization. So in simple terms, I will say that it helps in training the model over thousands of layers effectively. It consists of many layers, as if we compare it to AlexNet, which had 5 layers, and the LayNet, which had 7 layers. This has some thousands of layers, but it doesn't affect the performance in the long run. It and it bagged all the awards in our Indeed ImageNet competition 2015 for over the fields of classification, detection, localization. This is like one of the most important architecture currently. And then there's still many other models in architecture that people are working on. Like we have the model like Inception model, which was the winner of the 2014 ImageNet competition. It was developed by Google as well. So after discussing the different types of CNN, I think we'll be taking a break, not a not a like a huge break, a 5 minute break we'll be taking to refresh your minds after this. Uh, and after this, working, we'll be having the hands-on session. So do come after 5 minutes, and during this break, you can connect with us with our social media handles: Instagram, Twitter, LinkedIn. You can even send a mail to our data science community, and we have a YouTube channel as well, Data Science Community SRM. Do check those out, guys. Uh, so we'll be resuming this session. So we'll be going towards the interesting part of this session, which is the hands-on session. We'll be implementing this concepts that we learned in the previous slides into code. So like we'll be using the Google Colab, and so be ready with the Colab if you want to implement it as well. So my fellow co-speaker Harshit Agarwal will guide you guys.
Hello, can you guys hear me now? Okay, uh, I'm assuming you can. Hi guys, I'm Harshit, and we will be starting with a hands-on session. I will be showing you how to write a binary classifier from scratch. So I have shared the link in the chat box. You can try it out with me. So let's start. So first, as I said, we will be making a binary classifier in this hands-on session, and we will be distinguishing between dogs and cats. So first, you have to make sure that your runtime, your hardware is selected to GPU and then connect. All right. So first we import all our required libraries. We will be using TensorFlow and Keras in this. We will be making our model in Keras. Keras is a library in which all the layers and activation functions and everything is defined, which makes our job very easy. So let's start. And now we will be downloading the data set. So this data set that we will be downloading, it contains the images of cats and dogs in separate folders. So you can run it with me if you want. Right. Let's unzip it into our directory. Good. So when we take a look at our directory, we can see there's a folder called pet images. So this is our dataset folder. When we go into that pet images folder, we can see that there are two subfolders, cat and dog. So inside these folders are thousands of images of cats and dogs, which we will be using as our dataset for the classifier. So now what we have to do is, since this is an unknown, this is a foreign data set, we have to clean the data set. Uh, how we will be doing that is we will be deleting the corrupted files which are of no use to us. So in this block, as you can see, we are iterating through all the files in those folders, cat and dog. And if that file is not compatible, we are skipping that file from our data set. We are deleting it. As you can see, 1590 images were corrupted, so they are deleted. Now let's split the dataset into our training dataset and validation dataset. I'm taking the image size as 180 by 180, but you can change this if you want. you can do anything. Then batch size I'm taking as 32. You can also play around with this and see what works better. So as you can see, I am splitting the dataset into 80% and 20%. So my training dataset has 18,728 files, while my validation dataset has 46,82 files. Now let's take a look at our files, the images that we have, cats and dogs. So as you can see, these are just few images that our dataset contains, and they are all very random and very different from each other. One thing which you might notice is this ones and zeros above each image. So what these ones and zeros denote are their classes. So since this is a binary classifier, so the only two classes that we have, the only two classes which our model will output will be in terms of 0 and 1, where 0 means cats and 1 means dogs. So now we're going to do something which is called data augmentation. So what is data augmentation is we're creating more data from existing data. And how we do that is suppose we take one image and we flip it horizontally and we rotate it by 0.1 degrees, or that means 0.1 of 360. So immediately we get two more images out of one image. So we are literally creating more images out of one image. And what this helps in is the overfitting of the model, because we don't want our model to just, uh, recognize vertical, horizontal, and in a particular angle of images of cats and dogs. We don't want that. So we are getting a variety of pictures. And I have also provided a link here if you want to know more about data augmentation. So, okay, so over here, I'm taking an image. Let's see what happens to an image when it goes into data augmentation. We are augmenting an image 9 times, and let's see what happens. Okay, so as you can see, one of these images is the original image, and from one of them, we are getting 8 more images. So instantly, our data set increased by 8 times. So, I mean, that is very good. As you can see, all of these images are actually different from each other. Some of them are so you can skip this step, but what this does is makes the computation faster. So I'm going to do this. Okay, so now let's get to the model over here. And also, if you have any questions at all, feel free to ask them in the chat box. Okay, let's make our model. So I've created a function make model in which I'm taking two arguments, the shape, input shape, and the number of classes. Why I'm doing this, why I'm creating a function over here is the reusability of this code, is to provide reusability. You can essentially use this function for multi-class classification or any kind of other classification as you want. You can just change the input shape and num classes. So that helps a lot. This is just good practice of code. Let's start. So in our what is the input of our model? Again, whatever input shape we provide, we're converting that into a tensor, keras.tensor. If you remember, we imported a library no, as tensor. Sorry, keras. I'm so sorry, keras. And what this basically does is it has a subfunction. It has a function called input, and it basically converts our input shape, our image, into a tensor. So that image is now our input. And again, what we do here is I have directly made the data augmentation into a layer of our model. So we don't have to directly augment each image into the dataset, because that takes another n time. time complexity. So now we rescale it because we need to again input it into our convolution layer. So as you might remember from our theory session, a convolution layer is nothing but, okay, I'm not going to say it because you just learned it. I mean, you have a quiz later. So in this convolution layer, this 32 means in this layer, there are 32 nodes, and 3 is the means there are 3 layers because it is an RGB image. Strides 2 and padding, if you remember, you should remember what padding is. Okay, then I'm using another layer which is known as batch normalization layer, and what it basically does is it standardizes our input so that the model converges faster and it learns better. Then we're using a ReLU layer, which is an activation function. And again, as you can see, I have repeated this many times. I'm increasing the number of nodes in each time: 32, 64, 128, 256. So this architecture is very basic and what we call a vanilla architecture. So after this session, after this hands-on session, I have created another notebook in which we are using skip connections. And if you understand everything that is going on here, you can refer to that notebook if you want to tease your mind a little bit more. So as you can see, we are using another layer which is called separable convolution layer. So what separable convolution does is it performs the same task, but it computes the image faster, and it performs a depth-wise spatial convolution by which we get better results. So I'm using that over here, and then over here. Okay, so as you can see, this is the last activation layer. Uh, and since this is a binary classifier, the num classes will be 2, and the activation we will be using is sigmoid. But if it is a multi-class classification, then the activation would be softmax. This is very important, guys. Then we are using a dropout layer. You must remember what a dropout layer was from our previous session by Tejas. So I'm using 0.5 as the attribute. What this means is we are basically deleting 50% of the nodes in our network randomly. You might think this actually is destructive to the network, but it actually helps a lot in learning. And this is the last output layer in which the real classification happens. So what this does is we are using the activation, which is sigmoid, and units. That means the number of nodes that we want. That is 1 because the answer can only be 1, dog or cat, 0 or 1. So let's make this model and see what the architecture is. Okay, damn. I'm so sorry. I'm just gonna delete all of this. Yeah, okay. Okay, so this is the architecture of our model. As I explained, we have an input layer that goes through data augmentation, and then we rescale it. Then we have convolution layers, batch normalization, activation. I explained all of this to you just a couple of seconds back. Then over here, we have just one node which outputs 0 or 1. So now what we're going to do is we're going to train this model on our data set. Right now we have just created our model. Now we have to train it. So I'm not going to train it right now because it takes some time, but I did train it a while back in the morning, and these are the results I got. So I'm training the model for 5 epochs, and I'm using the Adam optimizer with with learning rate as 1e minus 3. You can change these hyperparameters as much as you want, play with them, see what happens. You may get a better accuracy than me. and it might be better. So you can play around with this. I got an accuracy of about 82%, which is quite nice for a binary classifier because I mean it's just a binary classifier. So then what we're going to do here is we're going to perform inference. What inference means is we're basically going to take a random image from our dataset. For this example, took an image of a cat, and then we're going to predict it using our model. So when I predicted it, the model predicted that it is 99.58% cat, and like according to it, it is 0.42% chances of being a dog. So this was a pretty good. This is a decent result. This is pretty nice. 82 at 82% validation accuracy. This is pretty nice. So that is actually all there was in the code. And you can play around with the hyperparameters, with the data, see what happens, remove data augmentation if you want, see how it affects the validation accuracy. And yeah, that's pretty much it. And again, I have created another notebook in which I'm using skip connections, and the data and the hyperparameters, everything is the same, just the model is different, and it is a very complicated model for some. And in that model, I'm getting an accuracy of 97%. So do check it out and see if you can understand it. I can't explain skip connections right now due to our time foundations, but maybe next time. So that's pretty much it. Thank you.
So I hope you all enjoyed the session we conducted. Like, thank you for attending this session, and we hope you have learned something and had a great time. Um, we have, these are the sponsors for the NeuRes community.
Uh,
Yeah.
yeah. So guys, thank you for staying till now. And after this, we have a 10-question quiz on the topics that we covered today. And the quiz will be taken through a Google form, and which the link would be sent in the newest channel of our outer circle. So all of those people, and the form will be open for a short time. So those who fill the most correct answers and at the same time quickly will receive swags from the sponsors, and the sponsors are purely based on the quiz results, and the form will open at 6:30 and it will remain open till 6:35, so stay alert for the form link. Thank you.
If you liked our session, today's session, we'll be we'll be continuing our this deep learning series on 22nd March, where my fellow colleagues from the data science community will be talking about RNNs and sequence models. Do join us on 22nd and follow our Instagram handle carefully. We'll be giving more instructions about this day 4 session as well. So, like, we'll be conducting the quiz in our Discord channel, like the NeuRes channel. Thank you very much, guys.
Hey guys, the quiz link has been posted and it's open to accept responses now. Yes, I mean it's open. It will accept responses now. Please try now. It will remain open for 5 Guys, the form is closed. Thank you for attending the quiz and thank you for attending the session. We hope it was useful for you. Thank you and have a good evening.